Hi everyone, my name is Archana Sinde, and today I'm going to be presenting about Intel Clear Containers. I'm a software engineer at Intel Open Source Technology Center, and I've been working on Clear Containers project for close to a year now. Recently, I've started working on the networking aspects of the project, and that's what I'm going to talk about today. So today I will give you an overview of Intel Clear Containers, what they are and how they can be used for network function virtualization. Then we will take a look at some data plane technologies like SR-IOV, DPDK and VPP. This will be followed by an overview of VFIO and the support that we've added in Clear Containers to enable these technologies. In the end, I will show you a demo of Intel Clear Containers with SRIOV and DPDK. So let's begin with an overview. Intel Clear Containers, let me mention, it's an open source project. You can find all the source code of it on GitHub. So containers, I'm sure most of you must have used containers in your developer user workflow. Now, containers are very popular right now. The whole reason they are popular is because they are they provide a nice way to package applications and to deploy the applications along with the entire dependencies. You can run the same application bundled in a container on any OS, say Ubuntu, Fedora, CentOS, or any distribution of your choice. You can go from pulling, say, a Docker image from a remote Docker repository, let's say Docker Hub, to actually getting to run a container. And typically running a container takes less than 1 second. The pull may take more than that. Now, if you compare this, virtual machines are generally packaged using virtual disks, which easily take like around 1 gigs of space on your disk. They also take time to bootstrap, they take time to deploy and run. So the ease of packaging and deployment is what make containers much more popular than VMs. Like I spoke on the previous slide, Linux containers allow you to isolate and package applications along with the entire runtime environment. And they do so relying on two kernel capabilities. One is kernel namespaces in order to provide the isolation between containers. And the second is C groups, which is used to provide resource isolation. So containers can access only the CPU or the disk that's allocated to them beforehand. So as you can see, while there is isolation between containers using namespaces and C groups, they still share the same kernel. The key takeaway is that if the kernel gets compromised by any application running in a container, it can potentially compromise all other containers running on the same host. So the point is, when you're going from security that is to containers, you're going from security that is built into hardware, usually it's Intel VTx, to security that is built into software. And in our case, it's the Linux kernel. So on the far end, you have virtual machines, which are slow to boot up and they are hard to deploy. And on the other hand, you have containers, which are fast to deploy and they're fast to start and they have all the packaging and tooling around them. So this is where Clear Containers steps in to fill the gap. With Clear Containers, you can deploy containers with the same tooling as regular containers, but the isolation and the security between them is the same technology that is used in virtual machines. So how do we do this? With Clear Containers, we actually launch a container in a lightweight virtual machine. So by virtue of virtual machines, every container gets its own copy of the Linux kernel. This also means that you can run the greatest and the latest kernel inside a container, while your host can run the same kernel that the distribution has provided for it. This means that because we are running a separate kernel, so if one of the applications compromises the kernel in a container, that exploit is restricted to that particular VM itself. It cannot transpire to the host, nor can it transpire to the other containers running on the same host. As I mentioned, we run the workload in a container, in a VM. We have used quite a few technologies in order to make sure that the VM boots fast. So how do we do this? In order to achieve the fast boot up, we used a lightweight version of QEMU that does not support any any legacy devices. It does not scan the PCI space, nor does it wait for legacy drives, like let's say a CD-ROM or a spinning drive to show up. We also use a very minimal version of the kernel, which is just enough to run the container workload. We run a minimal root FS, that's systemd based, inside the VM. And this systemd based root FS is mounted inside the VM using a combination of non-volatile memory, that is NVDIMM, and DAX. So DAX is something that's provided kernel that allows us to allows the guest direct access to memory pages of the root FS. So in this way, the guest can bypass the page cache, and this means that we have a low overhead on the file system cache inside the guest. Also, since the root FS and kernel, both of them are memory mapped, we can use another capability of the kernel, which is known as KSM, that is kernel same page merging. Now with KSM allows us to deduplicate memory across kernel and the root FS of multiple containers. So this means that is the overall memory overhead is low. So how do we integrate with Docker? I mentioned that we use the same tooling as regular containers. So this would need integration with tooling like Docker. With Docker 1.12, Docker added support for replacing the default runtime with an OCI compliant runtime. So OCI stands for Open Container Initiative, and it's a specification that is developed by Docker and others in industry to have a common specification for container formats and their runtimes. So clear containers, what we do is we provide and implement OCI compliant runtime. So you can install clear containers on any platform that runs Docker and replace the default runtime with clear containers. So by doing so, it's transparent to the end user. It's transparent to an orchestrator like Docker Swarm. So user and the developer workflow is unchanged, but a container is launched transparently inside a VM when we launch a container. So that was an overview of clear containers. So we have these fast and secure containers. But how is this? How does it matter from networking or telco point of view? So historically, virtual network functions have been implemented in virtual machines. Telco usage and requirements tend to favor VMs over containers, at least for the time being. When it comes to telcos, they require a high reliability usually, and they use customized kernels with highly custom kernel options in order to run their workload. And this is done to make sure that the latency is kept at a minimum. The use cases also aren't throwaway. So they are not like short-lived workloads that run in the cloud for a few seconds and then go away. They usually run for a sustained period of time. Now this is where clear containers is interesting, because since clear containers runs the container inside a VM, we can use all of the feature sets that virtual machines provide, like vhost, SR-IOV, and DPDK in order to implement virtual network functions. So here is a very simplified example of a virtual network function chain. We have packets that are coming in, and they are processed through a series of virtual network functions. Now, each of the VNF would do some kind of processing on the network packets, like they could be doing NATing or firewall or filtering of some sort. So how do we realize this VNF chain using virtual machines? So the question is, why not just implement the VNF chain that I showed earlier with the help of just regular containers and use the use the kernel stack for implementing VNFs. So with the traditional networking model, where when a packet is received, an interrupt is asserted. That interrupt is then serviced by the CPU. The CPU stops doing what it's doing and then goes and services that interrupt. And eventually, after a series of operations, data is finally copied from kernel space to user space. But with the evolution of Ethernet cards and as the line rate of the Ethernet cards has increased, this interrupt-driven packet processing has proved to be inadequate. This because a bulk of the time is consumed in getting packets in and out. So let's say for a 10 GB Ethernet card with a 64-byte packet size, this would mean around 15 interrupts per, 15 million packets per second, and that would translate to 15 million interrupts per second. So actually the requirements for packet processing for VNFs, which take place at high packet rate, they really make traditional networking model not a viable option anymore. So this slide basically shows what are some numbers on the time budget for packet processing. Now for a 10 GB NIC card, in order to maintain a 10 GB base throughput, through some calculations, we know that the time taken to process a packet that we can allot is around 67 nanoseconds. And on a 3 gigahertz CPU, this would roughly translate to 201 cycles. Now, if you compare this to the time it takes to access L2 and L3 caches, it's around 12 to 44 cycles. So if the packet is found in the cache, we're good. So we can complete the operation within 60 cycles. But if it is not, if it's a cache miss, then the time it takes to access memory is around 70 nanoseconds, which is around 210 cycles. So this has already gone over the limit that we have allotted for processing a packet. There are packet processing frameworks like VPP and DPDK. And so they prove to be highly efficient in doing packet processing in user space because they kind of amortize the cost to access memory over a larger number of packets. And let's see how they do that by taking a brief look at some of these frameworks. So let's take a look at DPDK. So DPDK stands for Data Plane Development Kit, and it's a framework for fast packet processing. With DPDK, the packet processing is moved from kernel space to user space. So with DPDK, we usually have a user mode driver that is continuously polling on the control registers. And so even though it's polling on the control registers at a very fast rate and the packets are read directly from the NIC. So you would say that polling is consumes a lot of CPU, but even though it consumes a lot of CPU, you can, if you have packets like the packet rate of tens of gigabits per second, it is much more efficient than waiting to get an interrupt. So polling is bad when the packet rate of the NIC drops as you are busy waiting for the packet to arrive. But with VNFs that run with like really at full capacities at a high packet rate, polling is a non-issue. So in case of DPDK, packets are read directly from the DMA area to avoid any copies. And they also make use of huge pages. Huge pages in the size of, let's say, 2 MB to 1 gig are used in DPDK applications. And this is because when you use huge pages, you typically use a fewer number of pages, and this means less misses in TLB. So this reduces the overall TLB overhead as well. VPP is another packet processing framework meant to efficiently process the packets. So VPP uses similarly like vector processing instead of scalar processing. So what this means is that at runtime, VPP grabs all the available packets from the RX string, and it forms a frame or a vector that they refer to. And this vector is then run through a packet processing graph. The graph is applied node by node to the entire packet vector. And every node then performs a specific operation on the vector. So, and one of the input nodes to this graph can be DP, as you can see in the diagram, it can be a DPDK input. So how does VPP solve the problems that we seen earlier? So VPP, as I mentioned, processes a vector of packets, and as a result, the cost of instruction cache misses is amortized over a large number of packets. So this solves the iCache trashing problem that we have in scalar packet processing. Graph nodes are themselves optimized in order to fit into the instruction cache, and the packets themselves are prefetched in order to in the data cache in order to reduce the data cache misses as well. Also, I like to mention here that VPP is like an extensible framework, so you can have plugins which introduce new graph nodes. They can change the graph, the way the graph is structured, and the way the packets are processed at runtime. So VPP can also, it's a highly extensible framework, and it can be used to build any kind of packet processing application. It can be used as a basis of a load balancer, a firewall, or even a host stack. Now let's take a look at some of the networking support that's added in Clear Containers in terms of, let's say, it's VFIO. So first I'm going to talk about VFIO, which stands for Virtual Function IO. So inside a guest, you have an option of running a para-virtualized driver, like a VirtIO driver, instead of an emulated driver. And you do this to get better performance. But with this kind of software-based sharing, because the physical NIC is still shared among the various guests, the VMM has to implement some kind of a software switch. This switch is used to route the packets to and from the appropriate VMs to the actual physical NIC. What this means is, CPU overhead because of this software switching. And like as an example, with testing, it's shown that with a 10 Gbps Ethernet controller, you can achieve a maximum throughput of about 4.5 to 6.5 gigabits per second with this kind of, say, a para-virtualized driver like VirtIO NIC. So one way to solve this problem is to move away from software-based sharing to maybe just assign the NIC directly to the virtual machine. And VFI is something that lets you do that. So VFIO is a secure user-level driver framework for Linux. In layman's terms, VFIO can be considered as a technology to provide user space access to real PCI hardware. So in this case, device is given the virtual address of the guest, and the device can directly DMA directly into it. VFIO, as I mentioned, is a secure framework, and it uses Intel VTD technology to do so. So Intel VTD is basically an implementation of IOMU, and IOMU, its job is to translate the virtual addresses to physical addresses for devices. And IMU also makes sure that a device cannot write to the DMA area of any other device. So VFIO uses IMU groups to provide isolation. The IMU groups themselves are set up on the platform at platform startup by the IMU driver. And you can consider IMU groups to be the smallest set of devices, which can be considered isolated from the perspective of IMU. So one thing I'd like to mention is that with VFIO, a side effect is all of the guest memory is pinned on the host. This is because guest memory cannot be swapped if it's a DMA target. And in case of VFIO, we don't really know what memory is the DMA memory. So here's a screenshot of how a device can be assigned to a clear container VM. So in this case, it happens to be an Intel Q80 device. The LSPCI output from the first command shows all the PCI information of the Q80 device. The devices that we are PCI devices are interested in is with the PCI BDF 8400, and please note the device ID, it's 37C8. The following command shows that this device with PCI BDF 84 it belongs to the IMU group 43. So sys/kernel actually shows you all the IMU groups that have been set up on the platform. Now in this screenshot, what has been done is we've gone ahead and assigned the device with all of the Q80 devices. We have unbounded them from the host driver, and we have bounded them to the VFIO driver. In this case, it happens to be VFI PCI. So once this is done, the devices with their groups appear under dev/VFIO, and these are the VFIO groups. So with VFI support added to clear containers, you can now directly assign the device by passing the VFI group on the Docker command line. And as you can see, I've run a docker run --device command, and the --device option now allows you to pass a device. So when you pass a VFIO group, what the clear containers runtime does is it figures out the devices that belong to this VFIO group, and it goes ahead and binds all of the devices belonging to that group directly to the virtual machine that is running the container. So in this way, all of the devices are now available to the container without the host stack coming into the picture. So the key takeaway from this is that clear containers allows an application that uses, say, accelerator device or a high-end network device to deploy on any host system. And that host system should basically just support VFIO. It does not need to have any of the host side drivers or any of the accelerator stacks. All of the drivers can be provided in the kernel that is provided with clear containers. So with VFI, we saw that we can assign a device to a virtual machine, and you can get much better performance rather than using a paravirtualized driver. But with a platform which has limited devices, this could be a limitation in terms of scalability. So how do we solve this? Like SRIOV is an answer to solving some of the scalability problems that we can have. So SRIOV stands for Single Root I/O Virtualization. It's an extension of the PCI spec itself. What SRIOV does is it introduces the concept of physical functions and virtual functions. Now, physical functions can be thought of as a full-fledged PCI device that exposes the SRIOV capability to the platform. It basically advertises to the platform that it's a SRIOV device. And virtual function can be thought as a lightweight PCI device It lacks the configuration capabilities of the physical function, but it has all of the resources required for data transmission. Virtual functions have their own separate queues for transmitting and receiving. So with SRIOV, you can take a physical NIC and you can assign it multiple virtual functions. And then you can pass each of these virtual functions directly to a VM in order to get native performance. So this diagram just shows an overview of like how SRIOV device assignment takes place. So as you can see, this is Ethernet card with SRIOV capabilities. We've assigned the various virtual functions to this particular Ethernet card, and we've assigned each of these virtual functions to a VM. So when a packet arrives, the packet is sorted based on its MAC address. It's placed in its own separate pool depending on the virtual function. And this packet is then DMA'd directly into the memory of the guest. And we do this using Intel VTx technology. So data is DMA'd directly to and from guest. This means that the VMM or the hypervisor is removed from the process of moving packets from the NIC to the guest OS. So what this does is it provides of low latency, a high bandwidth path for packets to get into the VMs in and out. What this does is the performance that we achieve with this is comparable to bare metal, and you can achieve the line rate of the bare metal Ethernet. Clear containers runs in virtual machines, so they can easily leverage SRIOV, and they do so using the VFIO support that we've added and that I mentioned previously. So here are some more resources for describing SRIOV in details. So we have seen an overview of clear containers, and we have seen some of the packet acceleration technologies like DPDK, VPP, and SRIOV. So let's see how this all fits together now, how it can be leveraged with clear containers. So let's see, we wanted to achieve this VNF chain with virtual machines and eventually with clear containers. So this is one way of implementing the virtual network function. You have packets getting into the VM. So here, instead of using SRIOV, you're using something called vhost user. Now, vhost user is an implementation supported by VPP, and it's a means of injecting packets into the VM at the fastest rate possible. VPP itself has implementations for both L3 routers and L2 switches that are built using VPP, and they can serve as a means of getting packets into the VM and as quickly as possible, and also as a means to connect a series of virtual machines. So you can create VM pipes that look something like this. So you have a vhost user getting packets from the network card, pushing it into the VM, and another vhost user interface that pushes the packet to another VM. So in some of the places, like in one of the VNFs, you can perform an application like encryption and do some multiplexing to send the stream up. So this is how people construct their VNF pipelines. Now, a slightly faster way to do the packet processing would be like the first VM using SRIOV instead of a vhost user. So the packets then are routed to the VM directly from the hardware. Packets can be processed using the kernel network stack inside the virtual machine. If you need an application that needs the kernel stack. So inside the guest, you can see two regular network interfaces. One is for the SRIOV NIC, and the other is for the vhost user. And this is one possible way to construct the pipeline. So you have packets coming in from SRIOV, getting packets getting processed by the kernel network stack inside the guest, and then packets gets transferred to the next VM with the help of a VPP L2 cross connect bridge. So it sends the packets in user space at a fast rate using this L2 bridge. Now you can do things even faster. So you have packets coming in from the SRIOV NIC function. And once they enter the VM, say the kernel stack is not sufficient for you. You may choose to run a user level stack, let's say a VPP pole mode driver PMD or a DPDK PMD inside the virtual machine. So now you have packets coming in through SRIOV. They are getting processed in user space inside the VM, and then they are sent out directly from user space onto the host through the vhost user. On the host, the packets are then transferred between the virtual machines in user space using the VPP L2 bridge. And this is the most efficient way that you could chain the packets as compared to the previous two methods that we have seen. Now, because clear containers use virtual machines, essentially VMs, we can construct these kind of pipelines using a combination of clear containers, SRIOV, and VPP. So we have added quite a few support in clear containers for implementing VNFs. Let's take a look at that. So we have implemented a CNM-based plugin. CNM is again the network specification from Docker for specifying how the networking between containers. So we have implemented SRIOV plugin, and what this plugin does is that it assumes that the virtual functions have already been created on the host, and it then goes ahead and places the virtual function from the SRIOV NIC into the container namespace. So this works out of the box with runc. But with our runtime, what our runtime does is it detects the virtual function inside the container namespace. And once it finds out an actual network function instead of a virtual interface provided by Docker, the runtime goes ahead and passes this directly to the VM by means of VFIO. So the virtual function is directly assigned to the VM, and all of this happens transparently. So once you have the network created by the plugin, the runtime can automatically detect the virtual function and set up the network using this virtual function. Another plugin we've created is for PPP. So this plugin replaces the Docker provided default bridge that you see as Docker 0. It replaces that with a VPP-based L2 bridge. So this means that sending packets from one container to the next container happens extremely fast. So these are plugins, but we've recently added support for the features that may be useful from the networking point of view. So we've added support for pre-allocating memory. So in case of guest, the guest allocates memory on demand. But when we allocate memory beforehand, before the guest is launched, this means that there is extremely low latency for running applications. We've also added support for huge pages. Huge pages, like I mentioned, are used in DPDK and VPP, and with this configuration support for huge pages, you can configure them easily, and then you can have a DPDK app running inside clear containers in a matter of few steps. And all of this is, all of the plugins themselves are all open source. You can find them under Clear Containers repo on GitHub. So what's the difference between SRIOV and PCI passthrough? Now, SRIOV makes use of IMA groups. It's much more secure level. You can do the same thing with PCI passthrough, and I think PCI passthrough is just limited to x86. So So doing things through VFIO is much more secure. And specifically, you mentioned about SRIOV. You can pass virtual functions that have been created on a SRIOV device with the help of VFIO. Another question, does the VPP L2 bridge mean that I should restrict my VNFs to a single host? No, this can be run. So VPP provides L2 bridges, provides L3 routers, so you can very well have containers running on several machines. What are the advantages of using SRIOV compared to DPDK? So with SRIOV, what you're doing is you're passing your actual physical device, in this case a virtual function, to your VM. And so there is the host stack does not come into picture here. And DPDK is a packet processing framework that you can then run inside the VM. So SRIOV is useful in terms of virtualizations. It's meant for passing your physical functions or virtual functions to VMs. So DPDK can be used to get packets from an SRIOV virtual function. It can be run on the host as well as the guest. So if you have the physical device available directly on the guest, you can very well run a user stack with DPDK on the host. So SRIOV and DPDK, like, they play together. Thanks everyone for attending.